Okay, I think that was the people. Yeah. Hi, my name is Donguk Kim. We're team number 16, and our task was the aorta segmentation with transformer-based visual models. So this is our outline. We'll do a quick motivation check with the related works, and then introduce our data set, and how then the methodology with the results and conclusion. So our motivation was our motivation for segmenting the aorta was just aortic diseases such as the abdominal aorta aneurysm. It's basically a bulge or swelling in the aorta and the main blood vessels that runs from the heart down through the chest and tummy. So it could be very dangerous if it's not spotted early on. So yeah, our original task was actually a competition for the SNU hospital. Yeah. So yeah, we participated in the medical big data competition with the topic of PT and CT aorta segmentation. Unfortunately, we ranked 11th out of the 37 teams, so we weren't able to compete in the finals. So we had to change our data set to we had to change our data set in the middle of our project. So before we dive into the our model, I would like to just share a few related works. So UNet 3D, I'm sure all of you guys know, is kind of the baseline for most medical image segmentation tests, and especially for the aorta. During our research, we learned that the mask RCNN has shown comparable results in measuring the calcification of the aorta, and also other deep learning methods provide quantification of hemodynamic features such as the aortic flow and velocity and whatnot. So the data set that we use is the BTCV data set. It's a public data set that was out in 2015. So it's basically abdominal CT images that includes 50 images with 13 organs. But but for this test, we erased all the other labels except for the aorta labels, and yeah. So basically, what we wanted to do is we used the unit R as the baseline, and unlike previous approaches, we wanted to try out transformers as encoders. So previous models, like the unit, many medical image segmentation tasks use convolutional neural networks as the encoders and also for the decoders. But the unit R proposes the using transformers as the encoder, and then use the normal unit structure for decoding and getting the output. So what we wanted to add on to this baseline was first we were thinking about inception blocks, and inception blocks in our version, it consists of 3 parallel blocks that add to each other to let the model have a better view of the orthogonal contextual information. So one will be the axial, one will be the sagittal, and one will be the coronal. And the leftmost branch would be there for just dimension reduction. And we thought that this would improve the orthogonal contextual information understanding and also reduce the computational complexity, because we figured that the transformers were pretty heavy when during training. So this is the model that one of the models that we came up with. It's basically just the same unit R baseline, but added a inception block in the middle, and also removed all the convolutional removed all the 3x3 convolutional layers and substituted with the inception blocks. And the second model that we thought of was using attention gates, which allow each model to learn which information is important among feature maps from skip connections. So it just has a residual form, and it takes a feature map, an activation level map as an input, and then takes both activation functions and resamples by trilinear interpolation. So this was to just see how much it improves the accuracy of the previous unit R-based model. So yeah, we added attention gates when concatenating with the skip connection. So for the metrics, we used the dice score, which you guys probably all know. So the results came out as we didn't quite achieve the results that we wanted to get. First of all, we trained in 2 different environments, and the transformers as encoders were extremely heavy. So the inputs were pretty big, and in order to get reasonable
Sorry,
scores.
6 minutes is over. Please finish in 1 sentence.
Yeah. So if the computing power, if we had more computing power, we could have had more iterations to learn because the loss didn't converge at the end. So there's more room for this model to improve. Yeah, that would be all. Thank you.
Okay, thanks. Any question? Okay, thanks.